Hello guys, another important problem here. This is the 8th problem from our TFR series. We are solving TFR GS 2010 section A, problem number 8. So this is a capacitance chapter problem. It is saying two parallel plates of metal sandwich dielectric pad thickness D forming an ideal capacitor. The dielectric pad is elastic with a spring constant K. So when an ideal battery of voltage V is connected across the terminal of the two plates, there is a fractional change in the gap between the plates. So what is that gap? Now if we just draw to understand the physicality of the problem, there are two plates like this. These plates have been connected to the battery. So obviously when you connect the positive terminal of the battery to a metallic plate, electrons will start moving here and the current will flow here. This is suppose a positive charge accumulating on this side, correspondingly negative charge will be accumulating on this side, right? So you have to so this behaves like an ideal capacitor. Now also for a metal plate, when you induce a voltage like this, so because they are elastic and behaving like a spring also, which they have mentioned with spring constant K, so it will be due to this voltage induction, although it's very small initially, but they will experience a force towards each other because also they're elastic. So there are some formulas that we need to begin with. The first formula is F is equals to K into X, which is the spring force. This is from the Hooke's law. And another from the electrodynamics that we know, F is equals to F by Q, or charge is equals to E. This is our electric field, induced electric field, right? This is 2, this is 1. Now simplifying this second equation, what we can write here is so F is equals to E into Q. Let us take the magnitude of this electric field. So again, from the Gauss law, if you know, E is equals to sigma by 2 epsilon naught for 1 metallic plate. One means on one side of one metallic plate it is sigma by 2 epsilon naught, and on both sides it will be sigma by epsilon naught. This is also very important derivation. We are using this relation. If you want to know how this comes, you can just leave a comment. I will explain it, but yeah, this is an important relation. So F will be sigma by 2 epsilon naught into charge, and this charge can be again written as sigma into A. Why? Because dq by dA is equals to sigma. Sigma is the surface charge, differential surface charge accumulation. This is sigma square A by 2 epsilon naught, right? Now you equate this equation with the Hooke's law equation. So you can write from here only sigma equal to K into X, right? Now find X because we need a differential gap. So sigma square A by 2 epsilon naught K. So A is constant, epsilon is constant, K is also constant, right? The dielectric nature of the particle. So now what we can do, let us think what we should do here. It's So can we write this sigma square as charge by area? Just replace this relation here. What will it be? It will be q square by 2 epsilon naught k into a, right? The k is a spring constant also. Don't mistake it as dielectric constant. We sometimes write in k also dielectric constant. So dielectric constant means not like epsilon part. We write k is equals to 1 by 4 pi epsilon naught. We represent like this in the Coulomb's force, but not in this case, right? Let us mention it just for any misunderstanding. Spring constant. Now this is equals to, again, okay, another relation we need to induce here is this capacitance of capacitor. How do we define it? As it is defined as q by v, right? Charge accumulated per unit voltage, that is the capacitance definition. So q square will give us c square v square by 2 epsilon naught ka. Now if this x, we write it as del into d, which is the differential length that the changed in the capacitor when the battery is connected. So how the main equation will change? It will change like this c square, we can again write it as epsilon 0 a by d minus del d square. Okay, now this might look a bit confusing, like how did it come from out of thin air? So what is the capacitance depending on, like in physical terms? It's obviously charged by voltage, but again it is depending on the dielectric constant of the substance that is between the plates. In this case it is air, so it's directly proportional to that. It is also directly proportional to the area, because the more the area of the plates, more the charge it can hold. Also it is indirectly proportional to the length, right? Because what is length? Okay, this is not the square, my mistake. This will be just del by del d. Here it will be depending on the length between the plates, because if you increase the length between the plates, what will happen? The charge has to travel a long time, I mean the longer distance, so some amount of charge might be lost there. So if you increase the distance between the plates, the charge the capacitance decreases. So like that, it is epsilon 0 by d minus del d. Here we have written del minus del d because we have to find this del d part. Del d is nothing, just a small differential change in the distance between the plates. Now so replace c from the previous equation by this, so it will be getting epsilon 0 a by d, one will be cancelled, I think, right? Epsilon 0, yeah, in denominator also it will be cancelled, so epsilon 0 into dv square by d minus del d square dot d and 2k. We have adjusted with the d in numerator and denominator, you will see why. So this again, this epsilon 0 a by del d, this is again giving us capacitance, just to bring back the capacitance, because it is in the final form in the options, that's why we need it. And v square we have by d minus del d square into d by 2k. Okay, this is the final form. Now this is del D, but they have asked us to find del D by del, another del. So this is I mean like an operator here. So what is the differential change of differential, like that we can say this. So this 2 will go up, this will be half cv square by k d minus del d square. Now this del d square, you see, what is this I mean how this del comes actually is that we have considered this d is very small here, so this is del. Now if del d is very small change, you can assume it to be like d minus del t whole square, that is equals to what? That is equals to d square. This del t is you can take it extends to 0 almost, very small change, so you will get half cv square kd square. Okay, just change it like it, and you will get this form, half cv square by kd square. So let's check which option matches. It looks like option B matches with our answer, so this is the correct answer. Also very crude assumption regarding this problem. When I saw this problem, the first thing that struck my mind is that the differential change between the plates cannot be negative. I mean the plates cannot cross each other. At most it will be 0, but it will not cross each other. So yeah, I mean the negative options can be cancelled, and for the 0 plate, I mean it cannot be 0 also, right? Because if it's the differential change is absolutely 0, so it will mean that there is no capacitance only, it is behaving like a normal conductor. The plate, there is no gap in between the plates, so this is a normal conductor. So it has to be for the capacitance to exist, there has to be a minimum difference. So option B will be the right option. I mean without calculating only you can guess it, but the calculation is important. So thank you for watching, we'll meet soon. Keep sticking around with Bhautik Shastra and share with your friends. Thank you for watching.